Why does modern concrete crumble in just a few decades, while Roman concrete has survived for 2,000 years? We're talking about structures that have endured earthquakes, constant saltwater exposure, and the relentless march of time. The Pantheon's dome in Rome, the largest unreinforced concrete dome in the world, is still standing. Roman harbors are literally stronger today than when they were first built. So, how did the Romans pull this off? And more importantly, why did we forget their secret? Stick around until the end, because this ancient knowledge could completely revolutionize the future of construction. Around 300 BC, Roman engineers developed a building material so advanced that even modern science has struggled to fully understand it. This wasn't a lucky accident. It was a masterful combination of chemistry, geology, and pure genius, centuries before modern engineering even existed. This is the incredible story of Roman concrete. Let's talk about our modern concrete first. It's strong, for sure, but it has a built-in expiration date. Over time, water seeps into tiny pores. The steel rebar we use for reinforcement begins to rust and expand. This creates pressure from the inside, causing cracks to form and spread. That's why most modern structures are only designed to last about 50 to 100 years. But the Romans didn't build with steel reinforcement, and they didn't use our standard Portland cement. They had something far, far better. The primary secret ingredient was a special type of volcanic ash called pozzolana, named after the town of Pozzolani near Mount Vesuvius. Roman builders mixed this ash with lime and seawater. And this is where the magic happens. When seawater seeped into cracks in the Roman concrete, it didn't weaken the structure, it actually triggered a chemical reaction that made it stronger. New, incredibly durable minerals like aluminum, tobermorite, and philipsite would crystallize and grow within the concrete, filling the cracks and reinforcing the structure from the inside out. While modern concrete cracks under pressure, Roman concrete literally heals itself. But the story doesn't end there. Just recently, in 2023, scientists made another shocking discovery. They analyzed samples and found tiny white chunks called lime clasts scattered throughout the mix. For years, experts thought these were just signs of sloppy mixing or poor quality material. They were wrong. These lime clasts were intentional. When small cracks formed and water got in, it would activate these pockets of lime, creating a calcium-rich solution that would quickly recrystallize and seal the cracks shut. The Romans had invented self-healing concrete 2,000 years before we even conceptualized it. So if this technology was so brilliant, why did we ever stop using it? The short answer is, the Roman Empire collapsed. With it, centuries of knowledge, written records, and trade routes were lost. The specific recipe was forgotten over time. Plus, Roman concrete has a very long curing time, taking weeks or even months to set properly. In our modern world of rapid construction and tight deadlines, that's just too slow. But now, as we face a global crisis of crumbling infrastructure, rising repair costs, and the urgent need for sustainable materials, engineers are finally looking back to this ancient wisdom. Imagine if we could adapt Roman concrete for today's world. Buildings could last for centuries, not just decades. We'd have far less waste from demolition and rebuilding, and dramatically lower carbon emissions from cement production. The key to a more sustainable future might not be a new invention, but a rediscovery from our distant past. If ancient technology can still outperform modern science, what other incredible knowledge have we lost? Subscribe for more stories about ancient mysteries and forgotten technologies. Give this video a like if you were as shocked as I was. And let me know in the comments, should we rebuild our world using Roman technology? History isn't dead, it's just waiting to be rediscovered. Thanks for watching.